Welcome to another demo session here from Introspect Technology on PCI Express testing. In this demo, we'll talk about transmitter testing, and we'll show the sequence of events that take place to perform complete TX eye diagram and voltage measurement testing, among other things. So the setup on the right-hand side here is the same as before. It has a device under test sitting on a CBB. This happens to be an 8-lane device and connected to all 8 ports basically of the SV1C, both the pattern generator ports shown here on the right-hand side as well as the pattern detector ports. And so to perform transmitter testing, we have written this automation script where we could enable transmitter testing after device identification. So we'll perform device identification, and then by clicking true here on this SI test option, we're able to ask the SV1C to perform a complete transmit test sequence. So we will click run here on the test procedure. And just like in previous sessions when we talked about device identification, we always recommend that the device is always identified with this step here to make sure that all lanes are connected, to make sure that the device does not have any defect that precludes it from being measured properly. And so we're performing this device identification step, which will take about 30 seconds. And then we'll get into the actual TX measurements. And so device identification has just finished, and now we're entering into the TX measurements. And we'll be performing these TX measurements on a couple of the toggle rates for the device under test. And so this green line here, sending toggle, is really informative for us, telling us that the SV1C has asked the device to toggle from Gen 1 to Gen 2. And then we're performing some measurements here, starting with analog waveform capture, and then followed by jitter measurement and eye diagram capture. So the SV1C is currently accumulating waveforms across the 8 lanes of the device at Gen 2 speed. And in a second or so it will finish, and we will proceed to the next step of the measurement. And so the SV1C has, after finishing the analog waveform capture, it's gone on to measure bathtub plots for the purpose of jitter measurement. And now it's doing simultaneous eye diagrams across all lanes as well. So the Introspect SV1C has finished testing one of the gen speeds for the device under test, and then it sent another toggle command to perform testing on the at the other speed and the other presets. So to perform the same sequence of events really as the last one, So while it's running, we can look at some previous results here to look at the kinds of waveforms that will be produced. And so this is an example of an analog waveform that comes out of the device at Gen 2 speeds. And you can just pan out here and see the entire waveform being displayed. And one of the things to notice about the waveform, of course, is the variability between lanes, and that's critical for making sure that the IP or the device under test is well characterized across lanes. And so the blue channel here is channel 1, and it clearly has a higher amplitude than, let's say, channel 7, for example. This is purely a device variation from one lane to the next, and one of the important things about the SU1C is that it's able to actually measure these lanes simultaneously and help you identify the various effects on across lanes. So this is a waveform measurement, and we're showing here just the waveform within a viewer for a quick, human read of the data. But of course, parameters like overshoot and voltage can be measured, and as well as rise time can also be measured. And then the other type of measurement, of course, is the total jitter measurement. And so, again, the SU1C is able to display all bathtub plots simultaneously. The plots themselves are divided into two parts. One is the actual measurements. So these are true BER measurements across phase for the device. And then the dotted graph is an extrapolation based on the Dirac delta model. And then finally, of course, the eye diagram plots are displayed here. So this is a pre-emphasized eye diagram, which is expected for PCI Express. And it's shown here on one channel. And of course, we could scroll through the different channels to tell the performance. And again, just like on the analog waveform, we could see some amplitude variability across lanes for this particular device. The device is also able to perform BER testing, which is a true BER count within the eye that goes to very deep levels. So we can display a logarithmic graph and look at error rates down to the 10 to the minus 6 or 10 to the minus 8. Okay, so my current run has just finished. As per this pop-up on the window. So this run has just finished right now, and it's taking me to the results view. And again, within 6 minutes, we have done characterization on all 8 lanes simultaneously. So this is the result that I just got right now. And so we can see, again, the waveform. That's the same as the waveform that we looked before. But you'll see that there was another analog capture displayed here. And that's because we have measured the device on 2 different pre-emphasis settings as per the PCI Express spec. And so one of the lanes, one of these captures has different pre-emphasis. We can look at them side by side like I'm doing now here, if I just display them side by side. Or more appropriately, we could actually click and drag the waveforms on top of each other. So if I just make these waveforms bigger again, and then I could click on this icon here and drag it into the other window and get a live comparison between the two captures. So this is the first lane with a clear distinction between the pre-emphasis levels, and the second lane, third lane, fourth lane, 5, 6, 7, all simultaneously. So we have shown here the ability to measure the multiple lanes very, very quickly across a single automation platform, using a single automation platform, and within minutes we're able to decipher differences between lanes and their performance.